Hello, Mr. Price here, and this is the second video of the June 2005 Mechanics 2 paper. This one will feature just question 2. Let's go straight into it. Okay, so here's the question. A particle is projected horizontally with a speed of 6 meters per second from a point 10 meters horizontally from the ground. The particle moves freely under gravity, and we want to find the speed and direction of the motion of the particle at the instant it hits the ground. Okay, so what we're ultimately going to want to do is the very second it hits the ground, we want to know its vertical and horizontal speed, and then we can use trigonometry or Pythagoras to work out its angle and final speed at the point it hits the ground. Okay, now, first thing I'm going to do is just model my question. So, here is my particle, and it is projected 10 meters above the ground, like so, and it's fired perfectly horizontally at a speed in the x direction of 6 meters per second. So what's going to happen is the only force that's acting on my particle is gravity in the vertical plane. So that means my horizontal speed is going to be constant. So first thing I need to do is find at what time is it going to hit the ground. Okay, because this is going to be important so I can see how fast it's travelling. In fact, I don't even need this. I don't need the time. So I beg your pardon. I don't need the time because I just want the final speed at the point it hits the ground. Okay, so if it hits the ground over here somewhere, I want to know how fast it's travelling in this direction and how fast it's travelling in this direction, so that I've got a triangle here which I can then work out its final speed in that direction with an angle. Okay, so I just want a speed once it hits the ground. So, using suvat, because it's falling at a constant acceleration, I know that u in the y direction is 0. I'm only dealing with speeds in the y direction because that's where my acceleration is. My velocity I want to find out, so I can fill in my triangle down here. The acceleration, I'm going to use a positive value, so effectively I'm resolving this way. So resolving downwards, so A is positive 9.8. And I want to know how fast it will be travelling once it hits the ground at 10 meters. So, using x equals ut plus half at squared, I can substitute my values. So 10 equals 4.9 t squared, and t equals 10 over 7. Okay, I'm doing this a slightly longer way. You might have chosen to do it in one step, but I've just got the time there just in case it's relevant. In this case we won't really need this, but that's in case it's relevant. So that's how long it takes to hit the ground. Okay, we can also use v squared equals u squared plus 2ax, and actually this is the only bit we need to do. We didn't really need to do this. So v squared equals 0 plus 2 lots of 9.8 lots of 10. So once doing that, you should find the velocity to be 14 meters per second. Okay, so now filling in my my velocity triangle, so I know that I'm just going to slightly adapt this just so it's a little bit more clearer for you guys. So my ball is effectively going to be travelling at a speed going this way of 6 meters per second and down of 14 meters per second. So it's going to be travelling this way at an angle to either the horizontal or the vertical. I'm going to find it from the horizontal because that seems to make sense. Okay, so I want this missing angle here and this missing length. So using Pythagoras, the magnitude is 6 squared plus 14 squared or rooted. And we should find this to be 15.2 meters per second to 2SF. And then using tan theta equals the opposite over the adjacent, so tan theta is equal to 14 over 6. So using inverse tan, theta should equal 66.8 degrees to the horizontal. And that's it. Job done. Nothing further needs to be done. Okay, hope that helps. We'll look at question 3. Oh, I'm sorry, I didn't quite move the page down. There we are. We'll be looking at question 3 in the next video.